This is Higher Physics Notes, Unit 1, Section 7, The Expanding Universe, and this is Part 2, where we look at redshift and Hubble's law. Well, you've now studied the Doppler effect, so you might reasonably think that if you had, say, a star or a galaxy receding away from you, like so, or indeed coming towards you, but let's focus on the receding away, that the Doppler equations would apply and that you could work out the change in frequency of the light waves that were coming towards you. Like that. Well, it turns out that the Doppler equations don't apply in cases of light, and without getting into the details, the fundamental reason is that light doesn't need a medium to travel through, whereas waves like sound and all the other waves that we meet do require a medium. And this lack of a medium changes the physics, and so we have new equations that we're about to develop when we're dealing with a light source moving away or indeed towards us. Well, we discovered at the beginning of the 20th century that the galaxies, in fact, were all moving away from us. Sir Edwin Hubble created his famous law, which explained that. And what he discovered then was that the wavelength of the light that we saw was redshifted. And you've probably heard of redshift. So what are we talking about? Well, imagine, let's just take hydrogen and let's look at its emission spectrum. So if we can think of the hydrogen emission spectrum, there are various lines. Okay, so we've got various lines, and we've got a couple down at the violet end. Violet. Something like that. We've got a blue one, which I'll pop in there. We've got a light blue one. Let's see, maybe something along those lines. And we've got a fairly distinctive red one down here. It goes without saying, this is very much an approximation. And this, of course, is the hydrogen emission or line emission spectrum when the hydrogen is at rest. So we can do this in the lab on Earth, and that's the spectrum that we get. However, if we view a star which emits hydrogen, and that we know emits hydrogen because we can observe the coloured lines produced by the spectrometer, and what we find is that the same pattern of lines is there, but they're all shifted a bit to the red end of the spectrum. So notice those two purple ones have gone a wee bit to the right. That blue one done the same. The light blue one similarly, and then the red one itself maybe sort of gone up there. Now if you look at where the previous rest lines would have been, these dotted lines give you the kind of indication. You can see that in each case the line has moved towards the red end of the spectrum. So this is the red end, and this is the violet end. Okay, so this shift of the line, here's where it would have been, is called redshift, because the line has changed in its wavelength and actually now has a larger wavelength when we observe this galaxy moving away from us compared to what it would have had. And of course they've all been shifted by a similar amount. So there's the shift on the blue line, the light blue line. There's the darker blue one, and so on and so forth. So there you can see the upper one's gone there and the lower one's gone there. So this is redshift. This is what we observe when we look at the light coming to us from the galaxies which we know are moving away from us. We know this is hydrogen because the pattern, the relative spacing and positions of the lines are all exactly as hydrogen is, but they're all shifted a little bit so that the wavelengths of all the lines are a bit bigger than they would be on Earth. So various equations have been developed to measure this amount of shifting of the lines, this redshift. Well, the first thing then is to get that equation established, and in order to do that we need to give redshift a name, and it's called Z, and we tend to be talking about galaxies here because it's the galaxies that are all receding from us. Well, the redshift Z for a galaxy receding from us is given by the observed wavelength, that's the wavelength we actually see, the shifted wavelength, take away the rest wavelength, that's the wavelength we know the line would have when it was at rest. So for example, all of these correspond to rest wavelengths, whereas these are all, in the lower one, these are all the red-shifted wavelengths. Anyway, the equation then is that the redshift is given by the observed wavelength, lambda observed, minus the rest wavelength, lambda rest, divided by lambda rest. That's often written as Z equals delta lambda, the change in wavelength, over lambda, over lambda rest. And that equation is on the list, and one that you should be familiar with. Well, let's do an example, but before we do an example, actually, this equation works for all situations, but there's actually a second redshift equation. So also, this only applies to non-relativistic speeds of galaxies. So for non-relativistic recessional speeds, we have an alternative equation that Z simply equals the velocity of the galaxy divided by the speed of light. So it's really just what fraction of the speed of light the galaxy is receding at. Now remember, relativistic speeds mean approximately 10% of the speed of light or greater. Let's do an example then to show you how these work. And as you're going through these, if you can pause the video, try and solve them yourself before you see the solution. That's a better way of learning. So, we observe a spectral emission line of sodium. This would be sodium vapor, of course, in a star within a galaxy, to be 589.0 nanometers, and that's when we're on Earth. So that's its rest wavelength. In a distant galaxy, far, far away, we measure its wavelength to be 601.2 nanometers. Now we can see right away that that's a bigger wavelength. It has been redshifted, so its wavelength has shifted to a bigger wavelength closer to the red end of the spectrum, because the red end of the spectrum is the bigger wavelength end of the spectrum. So find two things: A, the redshift, and B, the galaxy's recessional speed. So there we are. Solution. As always, list your variables. So the rest wavelength, lambda r we'll call it, is 589.0 nanometers. The observed wavelength that we actually see and measure on Earth is 601.2 nanometers, and so Z is our unknown. We've listed our variables now, and we state our equation. Well, to get the redshift here, we know the observed wavelength and we know the rest wavelength, so it's going to be the wavelength equation that we're going to use. So it's lambda observed minus lambda rest over lambda rest. Just calling observed O and rest R is perfectly fine. Now all the wavelengths are in nanometers, so let's just leave them in nanometers, and it saves us having to use the times 10 to the minus 9. So 601.2, take away 589.0, divided by 589, and we get a redshift of 0.02071. Okay, and strictly speaking, we've got 4 significant figures in our data, so we should have 4 in our final answer, and that's indeed what we have. Notice the redshift has no unit. Normally I'm always on at you about putting in units, but of course that's only when there is a unit to put in. Because it's a ratio of 2 wavelengths, the units of each wavelength cancel on the top and the bottom of the fraction. So redshift is a unitless quantity. It's just a ratio. Right, so that's the first part done. Let's do part B. Well, part B wants the recessional velocity. So if you're dealing with a redshift problem and you're looking for the recessional velocity, or the recessional velocities involved, you're going to be using the speed equation version of redshift. So let's list our variables. We now know the redshift, 0.02071. You need every significant figure there, incidentally. Speed of light, of course, in the vacuum or in air, 3 times 10 to the 8 meters per second, and the unknown velocity is v. Right, so we can use our second version of the equation. Z is v over c. It's really just the ratio of the galaxy recessional speed to the speed of light. So 0.02071 is whatever v is over 3 times 10 to the 8. You can see at this stage of the equation that the redshift is just giving us essentially the fraction of the speed of light that the recessional velocity is. So this velocity is 0.02071 of the speed of light effectively, because when you rearrange it you get this. Okay, so it's going to be a small fraction of it, and when you multiply those together you'll get 6.214, to 4 significant figures, times 10 to the 6 meters per second. So that's the recessional speed of this particular galaxy. Notice that that recessional speed is of order of magnitude 6 times 10 to the 6, which is less than a relativistic speed, less than 10% speed of light. And that's how we do these problems. Worth bearing in mind that it's a very common situation to have to calculate the redshift using the wavelength equation, as we did there, get the redshift z, and then use that newly found redshift in the velocity version of the equation to get a velocity of recession. And so to Hubble's law. Well, Sir Edwin Hubble did a lot of pioneering work in the 1920s when he observed the galaxies. The first thing he discovered was that they were all moving away from us. No matter which direction you looked in, every galaxy he saw was moving away. And when he managed to plot a graph of the distance they were away from us against their recessional speed, he discovered something very interesting. So here's the graph that Hubble plotted. There were experimental errors in his data, but there was no doubt it was a nice straight line that he was observing. So what he plotted, the origin of course, was the distance to the galaxy from Earth on the x-axis. Now I'm just going to put it in meters. He didn't use meters, but let's simplify it and put it in as in meters. And on the y-axis he plotted the recessional velocity, and we're just going to put it in meters per second. Again, he used different units, but we put them into the metric system in the SI system. So when he plotted his data, as you probably know, he found this. So I'm going to give you the perfect graph going through the origin. Let's put it in red. There we have it. He found that there was a nice direct proportion relationship between the distance the galaxy was away from us and its recessional speed. So quite clearly, the further away the galaxy is from us, the greater its recessional speed. So, mathematically speaking, you can look at this graph and quite easily see that the gradient which is the change in y coordinate over the change in the x coordinate. And if we make our initial point the origin, then we can basically say that that equals the recessional velocity divided by the distance away. In other words, the velocity equals the gradient of the graph times the distance. Now the gradient of this graph is quite important because there only is one gradient for all the galaxies. Therefore this is a physical constant and has become known as Hubble's constant, and it's called h naught. So we have our Hubble equation. V is h naught d, where v is the recessional velocity of the galaxy, and we're going to use meters per second. D is the distance to the galaxy in meters, and if you do that, you then get h naught being Hubble's constant, which we believe to be a constant over time and throughout the universe. And in the units we are using, it turns out to be 2.3 times 10 to the minus 18 seconds to the minus 1. That will always be given to you in the data page. Well, let's try an example using Hubble's law. So, a distant galaxy far, far away is found to have a recessional velocity of 6.2 times 10 to the 6 meters per second. So it's moving away from us quite fast. How far from us is it? Well, it's quite remarkable that we can work out how far away a galaxy is just by knowing its recessional velocity. And of course we could get that recessional velocity by using the Redshift equation. So we very rapidly gain a great amount of information about these galaxies using these relatively simple equations. Right, solution. So we've got h naught, which of course you look up, 2.3 times 10 to the minus 18 seconds to the minus 1. The recessional velocity itself, 6.2 times 10 to the 6, and the distance from us is what we're after. Well, it's quite easy. We just state our Hubble equation. V is h naught d. Pop in numbers. One number popped in. Second number popped in, and then d is our unknown. Well, a little bit of algebra. So the distance then turns out to be 2.70 times 10 to the 24 meters. That's quite far away indeed. And that's how we use Hubble's law. And that brings us to the end of part 2 of the Expanding Universe notes.